so who wants to ask the question, or what problem should we look at first?
I think, well, for most of us in mind, we've had issues with Thevenin's, and then really just the Bode plots and the two-port network, which we struggled with, and then everything else was fine.
So that's basically three problems.
Yeah.
And we'll start with Thevenin theorem first.
Yeah.
And then we will switch over to other two problems. Okay?
Yeah. Perfect.
Okay, so I'm looking at mock exam that I prepared for this year for students, and question 3 is about a circuit that needs to be solved using Thevenin's theorem. So let me just read the question first. Do you have a question? Wonderful, thank you. So question number 3, it says for the circuit shown in figure 3, determine the Thevenin's equivalent circuit. Now this particular circuit doesn't have very many elements. However, we need to pay attention which elements are there, because that will determine the path as to how we approach solving this problem. One thing that sort of jumps out first is there is a 4IR dependent source. So that means that the source does not have a value for current that is predetermined, so to speak. The current depends on some other current in the circuit, in this case IR, which flows through the 2 ohm resistor. So that's one thing that we need to observe. And then of course the other thing that we can see is that there is an inductor in the circuit besides resistor, which means that this is a AC circuit. So we will have to deal with complex numbers, and we will need to solve for voltages and currents in terms of their real and imaginary values and things. So that does make things a little more difficult, but nothing that we cannot really deal with. So the real sort of a difference here is that dependent source. So as I noted in the solution, because we have a dependent source, we must find two things individually. In other words, we need to solve the circuit twice. Now, what is Thevenin's theorem? Well, Thevenin theorem says that we can replace any circuit with basically series connection of a source and resistor, or in this case, which is a general case, it would be an impedance. So this source will have certain voltage, which is V Thevenin, and that will be, of course, AC source. And in series, we will have Z Thevenin. Those are the two terminals that we will have. If you look at the original problem, they would have these sort of designations as A and B. So really what's behind these two terminals, A and B, is a circuit that is given in problem, which means it has an inductor, two sources, and a resistor. So we want to replace those four elements with this equivalent circuit, and in that circuit we will have just one source and just one impedance. So according to the theorem, Thevenin equivalent source is basically simply equal to the voltage of open circuit. So voltage of open circuit is basically voltage that we will have between these two terminals A and B when those two terminals are open. So that's, let's say, easy to find, but on the other hand, we will still need to solve this whole circuit in order to figure out that VOC. Now, in order to find Thevenin impedance, ZTH, we can actually calculate that as VOC divided by ISC. So that's a ratio of two values. Now, if we find Thevenin voltage first, then we have VOC. That VOC can be plugged in that ratio for Thevenin impedance. So that's one part of it. However, we will still need to find this ISC. Now, ISC is found if we short these two terminals as a current that would flow through that short. So ISC is a current of short circuit. So having found both VOC and ISC, we can then calculate Z Thevenin. So that is basically our objective, to find those two separate values, or to solve the circuit separately to find them. So let's go back to the beginning. Now this is what we're looking for at the end. So at the beginning we didn't have the equivalent there. We had basically this circuit. So I'm going to quickly draw it. We have inductor, and that inductor is J4 ohm, and then we have this dependent source which says 4IR. So here's a question for you. If this is 4IR, is this a voltage source or a current source?
Voltage source?
Yes. Well, first you can tell by what we have inside. We have plus and minus. If it was a current source, we would have an arrow. So it is a voltage source. So just to want to note that even though this voltage of this dependent voltage source depends on current IR, which I'm still going to put here, the value is volts, which means that this 4 is really ohm. It's not just a unitless value 4. Okay, so then I come to this point, and then I have two branches. Let's say one branch goes through the resistor and goes back to terminal B. So this is my 2 ohm resistor R, and I have current IR that flows through that resistor. And then I have another branch which has this independent source, and that's a current source that pushes 10 amps in that branch. So I have redrawn this original circuit. I basically just flipped it, because this is normally how we end up with points A and B when we solve Thevenin's theorem. So you can do that. So I have this circuit. Now I need to solve this circuit twice. So the first solution will be when points A and B are open. So open circuit. And the objective is to find that voltage of open circuit. And then the second part will be when those two points A and B are shorted. So we will look at the short circuit. And then in that short circuit we will need to figure out this current ISC. Now, if you have open circuit and if you have short circuit, that just one little short that we make a difference from one to the other is going to make a whole difference, really. It's going to mean that we will have to solve this really from the beginning. So you cannot look at these two individual cases where if you find something here in one case, then you can use it in the other case. Now that's not the case. So really you need to distinguish these two as two completely different circuits. So let's now focus on this, let's say circuit 1. So in circuit 1, these two are open, therefore this short doesn't exist. So if that short doesn't exist, then we can say that the current that flows through this inductor must be 0. Is this clear? Yeah. Because if there would be some current, there would be nowhere for that current to go. It's simply a dead end. So
you would have no current flowing through that A branch and then B branch as well.
Well, A and B are points. If you're talking about the branch is basically from this node to this node. So this is the branch.
Yeah.
And because this branch is open, so the current, if we would to have current that flows through this point A, the current couldn't go anywhere from that point. So that means that no electrons can even enter this branch.
Same thing for B as well.
And the same thing for B. So basically from let's say this point on. So in this part of the circuit and in this part of the circuit, you will have no current.
Okay.
So I equals 0 in both of those parts. So really, the only sort of a place where you could have a current is this loop here.
Yeah.
So that's the first sort of a conclusion that we need to come to, and that help us, with the rest of the analysis. Now, just because I said that current in this branch is 0, that doesn't mean that the voltage is 0. You may still have voltage between those two. Now, if the current through the inductor is 0, then the voltage drop across the inductor will be 0. That's what I do know. So this is the voltage across the inductor. Let's call it VL. So VL must be 0 because VL is ZL times I. And I is 0, therefore this voltage across inductor has to be 0. Now we don't necessarily need to have that voltage figured out. So, actually we will, because you will see later when we need to find this VOC, we will need to have this VL. But that's beside the point. That might be quite obvious that there is no voltage across inductor because the current is 0. However, this may not necessarily be obvious. If you have IR flowing through this resistor, the voltage of this source will be 4 ohms times that IR. And it could be, and probably will be, non-zero voltage. So that voltage will ultimately affect this voltage of open circuit. So we'll get back to that one in a moment. So for now, we can just observe that current here and here is 0. Therefore, the only place where we could have current is this loop. Now, this current source pushes current of 10 amps. Let's say like here. So because this is a current source, it is independent current source. It determines the current in this branch from one node to the other. And because it's 10 amps, this current has to be 10 amps. There's no question about it. It doesn't matter if there's a certain element in series or not. It has to be 10 amps because of that source. Now, once you come to this point with that current obviously cannot go towards the point A because it's 0. So the only sort of direction where that current can go is to actually go back down through this resistor. So 10 amps flows into this node, nothing goes towards A, everything else goes down. So that means you must have 10 amps flowing down through that resistor R. And it flows through the resistor R, gets to this point, nothing goes towards B, everything goes up, and there you go. You have basically 10 amps circulating in this loop. So you can really conclude that without really writing a KCL for this node or anything like that. You can simply observe what's going on and come to a conclusion that there is some kind of a circulating current in this loop. Now that at the same time gives us the answer as to how much is IR. Well, IR has to be 10 amps. And it's also plus 10 amps because it's obviously in the same direction as IR. So that's the first sort of a piece of information that we have figured out from this circuit. the reason why we need that is because we will eventually need it for that dependent source voltage. Now, we might be ready now to write the equation for this voltage VOC. Now, in order to do that, we can, let's say, select a path. Sal, can you just grab my yellow, on the other side, the green marker, please? Thanks. Okay, so we need to write KVL for a loop. So, for example, we can pick the loop, in this direction or in the other direction. That doesn't matter. What does matter, we need to include this VOC because that's what we want to calculate. So that's the part of the loop. And then on the other side, we can either go through this source or through this resistor. Now, I don't want my loop to go through the current source because I don't know the voltage across that source. So I'm going to end up in a sort of a dead end if I attempt to do something like that. So what I'm going to do, I'm going to assume that my loop goes through this resistor, through this source, and back there. And let's say I take this direction. Again, it doesn't matter what direction you pick, but once you pick a direction, then you need to stick with that direction. So I have a loop that includes my VOC, so I can write an equation for that voltage VOC. So if I start, let's say, from point A, and I'm going down, I have this positive sign of VOC that I encounter, so I can say that plus VOC, and then if I continue, there's no voltage drop anywhere here. Those are simply 0 ohm conductors. But the first one I have here is resistor. Now for resistor, I may put plus and minus here just to indicate that really my voltage across resistor R is having a plus sign on the top. So now since I'm coming from the bottom, I hit this negative sign. Therefore, I need to write minus, and voltage is VR. Now, VR, I can write as VR. Well, let me do that, and then I'll deal with what VR is in the next line. So that's one. And then I have...
Sorry, Sasha. Would it have not made life so much easier for you to just write that down as a positive and then a negative?
Where do you want me to put positive and negative?
After the resistor. So is that because you're going to have a double negative? Is that why you've done it?
I normally like to put the positive for voltage where the current enters.
Okay. Yeah.
So I don't end up with a negative in the Ohm's law.
Yeah. Okay.
I could pick this to be positive and this to be negative, but then my VR will be negative current times resistance.
Yeah. Okay.
So again, once you pick the plus or minus, you're free to pick whatever you like. But after you've picked it, then you have to stick with whatever you picked.
Yep.
So I found it maybe more convenient to have plus on the top because this current, flows into the plus, and that's again my choice. It's not what it has to be. So since I picked plus here, minus here, then I end up with a negative VR as I'm writing this KVL. So the next voltage is voltage across this dependent source. So my voltage is again with the positive sign on one side. This is negative sign. So I can say negative because I'm again encountering negative. And then this is I'm not even going to give it a name. I'm just going to write 4IR. That is the voltage of that dependent source. So 4IR. And then the next one is this VL. So I put plus on this side. That's fine. So let's say plus VL. And then once I have that VL, then I end up back at point A, which means that I just need to write equals 0. So this is my KVL equation. And in that equation, hopefully the only unknown will be VOC. Everything else I can calculate, I can express in a certain way and then figure it out. One thing that I do want to take care of first is this VL. So I said that current through inductor is 0, therefore VL is 0, that means that this one is 0. So that one falls out of the picture. So I can say that VOC equals, now I can put these two terms on the other side, so I'm going to have plus VR. Now VR, according to the Ohm's law, is R times IR. So R times IR. Now that holds if my current IR flows into the plus sign. If at the beginning I assume that the plus is here and negative is here, then my current would actually flow into the negative sign, which would mean that I would need to use negative for IR. But I didn't do that. So this is now something that matches the signs that I assumed at this resistor. So VR is RIR. So VR goes on the other side, becomes plus VR, that's plus R times IR. And then this minus 4IR also goes on the other side of this equation, becomes plus 4IR. So IR, I can probably plug in the values right now, but I can also do something like this. So IR, and then I have R plus 4. Now IR, I already calculated here, that's 10 amps. So 10 amps goes into this equation. Resistance is 2 ohms. That's my resistance here. So I know that 2 ohms plus 4 ohms, that's 6 ohms. 6 ohms times 10 amps is 60 volts. Okay? So 60 volts is VOC, so I have calculated that, and VOC is my Thevenin's equivalent voltage. So I have one sort of piece of a puzzle done. So I can say that V Thevenin is 60 volts, and I don't even have the angle or anything. It's just a real number. So that's part one of the solution, so to speak. Now, in order to determine the whole Thevenin equivalent, we also need to find Thevenin equivalent impedance. We already know VOC, so we need to find ISC. Again, in order to find ISC, we need to solve this circuit anew. So it doesn't matter now what I did before. I can probably erase my KVL loop. I'm also going to erase this conclusion that I is 0. I'm going to erase this voltage of open circuit. So I cannot erase this green all the way, but it doesn't matter. So what I'm trying to find now is this current ISC. So now points A and B are shorted. So if the current would come to point A, it could go down. Comes to point B, it could go this way. So really now there is no sort of a conclusion anymore that these currents are 0. So this doesn't hold anymore. So if I have ISC flowing through this short, then my ISC will also flow through this inductor. ISC will flow through this voltage source. ISC will flow through this piece of conductor here, and also ISC will somehow need to flow through those two branches. But again, I don't know how is that going to work. So in order to find ISC, if you look at the solution, you can actually use mesh currents to solve this part. Now, in the solution, I have assumed that there is some current I2 that flows in this loop. So let me just pick the same nomenclature so I can use this solution. So this is mesh current I2, and then I can also have mesh current I1. because I have flipped part of this circuit. Actually, this is the same, but the other side is flipped. So this doesn't necessarily comply with the rule that we mentioned when we're writing mesh circuit. We said that these currents should both be, let's say, clockwise. Now that rule is not very hard rule because it only helps us if those currents are made in the same direction, but that's not mandatory. So I actually can have these I1 and I2, one going clockwise, the other one going counterclockwise, so that's fine. Now, when I pick those directions, I just need to make sure that I establish a proper relationship between those mesh currents and other currents in the circuit. So if you compare I1 and ISC, you will see that those two flow in the opposite direction. So ISC is negative I1. So that's something that I can write just observing those two directions. Also on this side, I have IR. Well, IR flows down, I2 flows up. So in this branch to this resistor, I can also write that IR is negative I2. If you look at I2 flows through this resistor and through this current source. So that's the loop for I2. Now I do know current that flows through this branch. It is just like in the previous example, because in this branch, the only thing that I have is this 10 amp current source, then I know that current through this branch has to be 10 amps up. So I2 also flows through that same branch, however it flows in the other direction. And so because I already know how much current flows through that, I only need to fix sort of the sign. So I2 is of opposite sign of that 10 amp current. So I can say that I2 equals negative 10 amps. So in a sense, what I'm saying is because of this current source, I actually have the solution for I2 already. I don't need to solve for it. I can just sort of observe and write that equation. So from two mesh currents, I would expect to have two equations with two unknowns, but in this case I can say I2 is already 10 amps, so I don't need to solve for that. Now if I know that I2 is has certain value, I can also write basically KCL for this node here. So in that node there, I can say that IR comes out of the node, and I have 10 amp flowing into the node, and I have ISC flowing out of the node, or I1 flows into that node. I'm not sure if you see that, but let me just make that node like this. So if you look here, I have I1 coming from there. So this is my I1. I have 10 amps coming from this source. And I have IR coming down. So what I can do is, I can say IR equals I1 plus 10 amps. So that's again KCL for this node. So 10 amps flowing in, I1 flowing in, and IR flowing out. And that's what I also have in the solution. Although in solution there are some minuses as well, but you'll be able to figure that out. So the important thing is I have established certain relationship between IR and I1. So now what I need to do is, because I know how much is I2, I don't have that equation, but I will still need to write equation for I1. Now, because this is a mesh method, we will write a KVL equation, and then I have a certain loop here. Now, the loop includes inductor, this dependent source, and the resistor. So really, if you look at that loop is same as what we had in the first part. So it's still going to be this same loop. Now, just because it's the same loop doesn't mean we can use the same solution or anything. So, but we need to sort of write it again, because things are going to be different. For example, VL is not going to be 0 anymore. So let's write quickly this equation. So I have here, can maybe shorten this by but not writing everything. So in the solution I have plus ZL I1. So this is ZL, I1 goes here. Now obviously I have plus for this on the other side, which is not here. So let me change this, because I can still do that. Let's assume that plus for this VL is on this side. Now what I'm doing now has nothing to do with the first part. So first part I already solved. Now I'm solving a second case, a second circuit. So I'm actually free to pick plus sign on the other side if I want to. So anyway, if I pick plus here, and I have I1 flowing in, then I can say that that voltage is ZL times I1. So ZL times I1 plus 4IR. So 4IR is simply a voltage. Because we encounter plus, I was obviously going in an opposite direction as well in the solution. So I can do that too. So I can go instead in this way, come back here. So plus ZLI1 plus 4IR, and then I come down, then I have plus R times IR, and then I'm back to the beginning, so I have equals 0. So I'm not going to write all that, because you have it here in the solution, so just follow how it's solved, because it does involve some calculation to get to the value of I1. So what I did here is I have expressed IR in terms of I1. So I have already solved that IR is I1 plus 10 amps. I plugged it in the equation, and then I solved that equation by I1. Now, how do you solve this equation? Well, you definitely need to know how to divide two complex numbers, because at some point I get I1 equals minus 60 divided by 6 plus J4. So in order to find that, I need to multiply both numerator and denominator by 6 minus J4. And then I end up with I1 being minus 90 over 13 plus J 60 over 13 amps. And then the final step is ISC is negative I1. So I just need to negate that complex number. So I'm going to get that the ISC equals 90 over 13 minus J 60 over 13 amps. So I cut out a little bit of writing here, but nevertheless I do have my ISC, and that is what I was supposed to find in that second circuit. So now I have ISC, I have calculated VOC before, I can plug in VOC here, I can plug in ISC here, so then I can calculate my Thevenin equivalent impedance. So again, you will need to be able to divide some complex numbers and so on, but eventually get a very nice number. It's 6 plus J4. So 6 plus J4 being a Thevenin impedance, and 60 volt being a Thevenin voltage source comprise the Thevenin equivalent. So now I can get rid of all of this stuff, and if I have those two here, that will be basically equivalent to each other. Nothing would really change. If I have a 60 volts voltage source, and this impedance is 6 plus J4 ohm, 6 plus J4 ohm, that means I have 6 ohm resistor, and I also have J4 inductor. So this is the Thevenin equivalent for the circuit. The main difficulty in this problem was that dependent source required you to separately solve short circuit and separately solve open circuit. You know, in a simpler version of Thevenin equivalent problems, you won't have a dependent source, and then you will find open circuit voltage, and then instead of solving again for a different short circuit, you would simply use the shortcut method where you switch off all the sources and then just find equivalent impedance.
No, that makes a lot more sense. I think where some of us were getting stuck on was we had the two effectively mesh currents when we were trying to find our current, and our biggest issue was trying to account for the two mesh currents, if that makes sense. And it just gave us the wrong equation where you had solved, especially in your VOC as well, you had IR bracket resistor plus 4, which is where I made a stupid mistake, but that cleared it out, which helps.
Okay, wonderful. So we're good with the Thevenin theorem?
Yeah, just more practice would be good. I need to go over it myself,
Right.
but that's good.
There won't be a Norton question in the exam? Because they're pretty much the same.
They are pretty much the same. Even if you have a Norton equivalent question, you can still find the Thevenin equivalent, and then just use one step at the very end. And in that step, you can calculate the equivalent current source that would represent actually the Norton equivalent. So this is a voltage source in series with the impedance. If I would have Norton equivalent, then I would have current source in parallel with an impedance. So how would you know the values? Well, the values first, the Norton impedance is same as Thevenin impedance, so that's 6 plus J4. So that's the only difference is instead of being connected in series, it's connected in parallel. And then as far as the source, now this is a current source, so you cannot say it's 60 volts. You need to divide it by current to get the current. So I Norton is V Thevenin divided by Z Thevenin. So that would be 60 volts divided by 6 plus J4. So you would need to multiply with 6 minus J4, 6 minus J4, and then you will eventually find how much in terms of amps is this. So that would be your IM.
They're pretty similar.
So again, you don't need to solve Norton equivalent by, how should I say, by following the procedure directly for solving Norton equivalent. You can solve for Thevenin and then just do this conversion. If that's easier for you.
That's good.